In the previous lecture, we have learned about stress as the first building block of mechanics of materials. This lecture is about strain as the second important physical quantity to study the effect of forces on the object. The forces acting on a body distributes internally. The intensity of internal force at any point inside the body is called stress. Recall that there are two types of stresses. Normal stress is caused by a force that is perpendicular to its section. If the force is parallel to the section, it is producing shear stress. The external forces acting on a body cause the movements of small particles of a body relative to each other that cause the body to deform. So deformation is another effect caused by the forces. But not any movement is deformation. The movement or rotation of the entire solid object, like the objects studied in dynamics, is not called deformation, because in those cases, the body keeps its shape and size, and the distance of the inner particles of the element remains unchanged during the move. Deformation reflects the relative movement of the internal particles of a continuous body that cause the change in the size or the shape of an object. Deformation could happen due to loading or other factors such as temperature change. Similar to stress, there should be a physical quantity to precisely measure the amount of deformation. Strain is the physical quantity that measures the intensity of internal deformation within a body. Any change in the size and shape that takes place in small element, like the one that is shown on the left cube, is a combination of a change in the length of the element and a change in the angle of the element. The change in the length of the element is caused by normal stress. An element that is subjected to a tensile force elongates along the direction of the force. But there is no change in the angle of the element. All corners remain intact. On the other hand, a cube element subjected to shear stress will distort. All sides of the cube would keep their original length, but the angles of the element at the corners would change. Similar to stress, two types of strains are defined as normal strain and shear strain. Normal strain is produced by normal stress and reflects the change in the length of the element. Shear strain is caused by shear stress and measures the change in the angle of the element. This lecture will focus only on normal strain. Shear strain is discussed in details in the next lecture. Now let's define normal strain. Consider a cube element with an initial length of L that is subjected to normal stress, and assume that the amount of elongation in the element is delta. Normal strain, which is shown by epsilon, is mathematically defined as the change in the length of the element divided by the initial length. So epsilon is delta over L. Strain is a dimensionless quantity because both delta and L have the same unit, which cancels out in the fraction. So it is unnecessary to distinguish between SI units and US customer units, as the parameter is unitless. However, in engineering, strain is usually expressed as inch over inch, or millimeter over millimeter, or sometimes it is simply shown by epsilon. All have the same meaning. Another note is that normal strains in a typical solid structure are very small. So instead of working with very small numbers, they are expressed as microstrain. 1 microstrain is equal to 10 to the negative 6 strain. The sign convention for normal strain follows the normal stress. The element that is subjected to a tensile force elongates, and the normal strain associated with that is considered to be positive. On the other hand, if the element is subjected to a compressive force, it gets shorter, and the associated normal strain is considered to be negative. Alright, after learning about basics of normal strain, it's time to test our understanding with some examples. I will provide a link to the second part of this video that discusses 3 examples on how to use normal strain in different problems.